All right, so welcome back after that brief break. So, in the previous part, we discussed the fact that we are looking for properties of the solution. We have expressed them in terms of properties of the matrix A, which represents the system. X dot equals A x. So express properties of the solutions in terms of properties of the matrix. But we also made the case that those properties, namely the Hurwitz properties, were not easy to formulate in terms of a convex optimization problem. And so we're actually going to take a slightly different tact and approach the problem of stability in particular, and we'll generalize this to all sorts of input-out properties later. Approach the problem of stability not in terms of those eigenvalues, which are very hard to compute and numerically ill-conditioned and non-convex and all sorts of nasty things, and look instead in terms of a proof structure, a property structure in terms of proofs, which is suitable for convex optimization. And that's the Lyapunov framework. Mr. Lyapunov also gets his name. Lyapunov, back in the I forget when he died. But he also gets his name on this, right? So properties of the solution in terms of Lyapunov functions. And Lyapunov functions are actually a proof mechanism for these properties. They're not really a property of the matrix itself, but rather a property of the solution. And we'll get into that. So let me just state, right, what the Lyapunov theorem says, right, how it can be used to prove stability, right. So it's really, you're probably familiar with it to some extent because you're familiar with energies and stuff like that. And so the concept is rather straightforward, right. So a Lyapunov function is any function. Lyapunov function here is any function which is positive for any value of the states, not equal to 0. Right? And when the state is 0, we generally require the function to be 0. Right? So that's a candidate Lyapunov function, actually, technically. So these two properties make a candidate Lyapunov function. And here we've got some sort of visualizations of Lyapunov functions for systems. So this is the function v of x. This is x1 and x2. This is x1 and x2. Let's call it x2, x1. And these level sets are, it's a 3D image of the Lyapunov function. So this is v equals 1, or 2, for example. Maybe this is v equals 1. Important properties, however, is it's always positive, right? E is greater than 0 everywhere. And here at the equilibrium point, that's x equals 0, it is 0. V of x equals 0. Right? So, okay, that's a candidate Lyapunov function, so that doesn't seem very useful. But it's again a proof mechanism, right? So the idea is if this is a valid candidate Lyapunov function, and it has the property that its derivative along solutions of the system. So if you plug in x of t here into the Lyapunov function. So if x of t is a solution, then if you take the derivative of the Lyapunov function, that derivative is always 0, right? Less than 0, sorry. And what that means is basically that the Lyapunov function is always decreasing along solutions of the system, right? So here, for example, in these plots, right, this is a solution of the system, and the value of this Lyapunov function is decreasing. Right? It may go in all sorts of directions, but it's uniformly decreasing as time goes on. Right? So here's another 3D plot, right? It's like the solution here is decreasing, and these are the level sets of the Lyapunov function, v equals 2, for example, v equals 1, right? As the trajectory moves along in time, the value of the Lyapunov function is decreasing. So if you can find a candidate Lyapunov function which satisfies this property along solutions, right, then the system, you can prove that the system is stable. It's a fairly straightforward proof. And so you can think about these as energies of the system, right? If the energy of the system is decreasing. But as I'll argue, that's probably not the right way of thinking about these functions. So this is the concept of a Lyapunov function. It's a measure of the size of the solution and that it should be getting smaller as time goes forward as you approach 0, right? And that's why we have v of 0 is 0, because eventually, right, if you get close to, if this keeps decreasing, it'll eventually get close to 0. So if v is 0, if v is 0, then you're at x equals 0. So v of 0, v of x equals 0 implies x equals 0, and then you're at the origin. Right? So this proof structure, this Lyapunov function, how does this help us? Well, it helps us in a couple of ways. So I'll talk about it in more depth later. But first of all, we note that these constraints here, right? These are constraints. So our variable will be v. And these constraints, well, this constraint is linear. And this constraint is it's an inequality, right? So enforcing that can be posed as a convex optimization problem. So that's why Lyapunov functions are going to be very useful for transforming system properties or proof structures into convex optimization problems. Okay. Now, as I'll sort of make this point lots of times, it's better not to think of Lyapunov functions as energy, right? Better not to think of the value of the Lyapunov function as the energy of the system. This works very well in sort of mechanical systems where we have these ideas of kinetic and potential energy, right? And the idea is here, the problem here is this in potential energy, right? So potential energy is not actually energy. So if you're just thinking in terms of a conservative system, right, kinetic energy is an energy, but what is potential energy? Well, in a conservative system, there's a well-defined notion of potential energy, but in most systems, there's not, right? So what's the right way to think about Lyapunov functions? So the right way to think of the Lyapunov function is it measures how much strength is it measures the size of this solution in its entirety. Right? So at a given moment in time, right, then we can think of v of t as the size of the remaining solution as we go off into time infinity, right? So how much strength is left in this solution, right? So in particular, right, so if we go back to that image we had here on the previous slide, right, you can think of the value of v of t here as the integral of how long this solution is, right? So obviously, as time goes on, the remaining size in this solution is getting shorter, right? So if you just integrate this length, right, the length is getting shorter over time, right? And so there's a natural Lyapunov function for any system which sort of measures the length of the solution left as it spirals into 0, right? And so that's actually a much better interpretation of the Lyapunov function, is the if you think of the solution as a whole, right, that as this x of t as a function, it measures the size of that function. In particular, you can think of, if you're familiar with LP norms, right, it's sort of the L2 norm of that solution, or the remaining size of the solution. So we'll talk about that more later. So important, of course, is that you can enforce these constraints on the Lyapunov function in sort of a convex way. So the set of candidate Lyapunov functions. So a Lyapunov function, for example, is a candidate Lyapunov function if it satisfies this inequality, right? And depending on how you parameterize Lyapunov functions, right, this can be a convex inequality. And then the derivative, right, well, that's actually not relatively straightforward to enforce as well. Here we have a nonlinear system. We'll talk more about nonlinear systems later. But we just we apply the chain rule, and we can find the derivative of this Lyapunov function fairly easily. It's just the gradient of the Lyapunov function, and this is so v d dt. V of x of t is just, by the chain rule, the gradient of v times x dot, right? Move the d dt into the derivative, and of course x dot is just f of x, so it's just gradient of v transposed with f of x. And so we can relatively easily find the derivative of Lyapunov function, and then we just have to constrain that to be 0. So this is much closer to a convex optimization problem. And you can do other things with this. For example, you can use this to prove local stability, right? So for example, local stability means that if you start inside any level set of the Lyapunov function, right? So if you start inside the set of points here where the Lyapunov function is decreasing, right? Any level set of the Lyapunov function inside the space where it's decreasing, right? If you start inside this set, you'll stay inside the set because the Lyapunov function can't increase, and so the solution can never leave that region, right? So this is, say, the point where v of x, x such that v of x is less than or equal to 1, for example. All right, so you can also prove local stability, so you don't actually have to prove the Lyapunov function is decreasing everywhere. Again, we'll talk about this much more when we get to nonlinear stability, so it's not too important at this point, right? So but it's important, for example, in the cases where the system has multiple equilibrium points. Right now we're in linear systems, so they always only have one equilibrium point. But then if they have in nonlinear systems, they'll have multiple equilibrium points. And so it allows you to find basins of attraction of each of those equilibrium points. So what are some examples of Lyapunov functions? So, for example, in the mass spring, right, systems, the one probably we're most familiar with, and we talk a lot about actually in this class, the natural Lyapunov function is, of course, a combination of the kinetic energy, 1/2 mv squared, that's v, energy, and the spring potential energy. Right, and again, right, I said don't think about it in terms of energy because, you know, what is potential energy? Well, these are just the potential energy is really just the terms that aren't the kinetic energy in the Lyapunov function, right? So here it's like where do we get kinetic energy to begin, or potential energy, spring potential energy to begin with? Well, we get it from the Lyapunov function essentially. So it's sort of a reverse kind of logic here. In any case, you can take the derivative of this Lyapunov function, right, and you get x double dot, and we just plug in for x double dot, and there's x double dot here. And in this case, we can some of these terms cancel out. So, for example, no, not that term. This term and this term cancel out, right? And so you just get this negative definite term indicating the Lyapunov function is always decreasing. Here we've got an inverted spring, or sorry, an inverted pendulum problem. Oh no, this is actually a regular pendulum problem, my mistake. And And so, we know that the dynamics of the pendulum, right, are given here, right? So this is theta dot, for example. Actually, yeah, and this is theta double dot, right? So that's the simple pendulum system. And we choose, in this case, our Lyapunov function given by, this is kinetic energy, right? Because it depends on velocity, theta dot. And this is, I guess we could call it potential energy here, which is sort of the height of the bob in the system. So again, you take the derivative of it, right, and then we get an x dot term here. X dot, x1 dot, right, is just x2, so that's x2 there. And we take the derivative of this. 2x dot is, then we plug in for the mg sine x1. And, because we've chosen these wisely, and this is an energy conserving system, actually, these two terms cancel out, and we just get 0, right? So v dot is 0. So v dot, in this case, is not strictly decreasing. So technically, depending on how you define stability, this could be interpreted as not stable. But I think we'll consider it neutrally stable, right? Because v dot is equal to 0. It's not increasing, but it's also not decreasing. Right, so that's the basics of Lyapunov functions. Again, when we come to nonlinear systems, we'll talk about this in more depth. Again, those examples, right? We talked about them in terms of kinetic and potential energy. Again, probably not a good way of thinking of Lyapunov functions, however, because, right, what is potential energy? Well, there's no generalized form of potential energy except in conservative systems. And very rarely are systems conservative. I mean, under gravity, yes, okay, we have a conservative system, but generally it's not the case. So we have to think about we want to think about Lyapunov functions more broadly as just any function which is positive. And so for example, here's a system which is not obviously conservative and has no obvious Lyapunov function. Right? This is a model of a jet engine from Morg-Reitzer. Right? It's actually a simplified from the PDE model, which is much more complex. But here it is, right? It's got two states, and what's the Lyapunov function for this? We have no idea, right? What's the potential energy in this system? There's no obvious candidate for potential energy. But it turns out in this case, convex optimization can yield a Lyapunov function, although in this case it's rather complicated. And actually, these are the level sets of the Lyapunov function. Here you can see the vector field. All the trajectories are going into these level sets, so that along trajectories of the system, right, the Lyapunov function is uniformly decreasing. So actually, this was stolen from Perillo. Actually, this was stolen from Sanjay Lal, who stole it from Pablo Perillo. And I always misspell how Pablo does his last name. So sorry if you're watching that, Pablo. All right. So this concept of Lyapunov functions, of course, is important. The reason we're going over it is because it allows us to, at least, well, in the nonlinear case as well, formulate the problem of the question of stability. This finding a Lyapunov function can be formulated as a form of convex optimization. And so we showed in the previous part of this lecture that a system is stable if and only if it's Hurwitz. And now we can show, furthermore, that it's Hurwitz if and only if there exists a positive matrix P such that A transpose P plus PA is less than 0. And that's if and only if, right? So that's important. So it's necessary and sufficient condition for stability. And now expressed as an LMI, right? There's an LMI because the variables here are P, right? And the form is of a linear matrix inequality. There's two LMIs. LMI, this is really LMI 2, and this is LMI constraint 1. Note that that's sign definite, so greater than or equal to 0 is not good enough. It has to be strictly greater than 0. Why is that? Well, because, right, if it was inequality or non-strict, right, then p equals 0 would be a solution for any system, and obviously that's a trivial solution, and it has no merit, right? It doesn't prove stability of anything. But computers don't know that, right? So unless you tell it it's positive definite, right, it will automatically always give you the p equals 0 solution. So if you're working on the homeworks and you're getting you're getting too many feasible solutions, look at p. Look at the value of p, and if it's 0, then you forgot to make your inequality strict. Right. Well, anyway, so I'll get away from that. But the important point, of course, is that this is necessary and sufficient condition for A to be Hurwitz, which is necessary and sufficient for the system to be stable. Now, how do we prove this, right? And again, I don't concentrate too much on proofs in this course, right? Because we're trying to do something useful. We're trying to set up these optimization problems. But why did I talk about Lyapunov functions if, right, we don't use them, right? And so this is sort of the simplest case of how the Lyapunov function allows us to translate a system property to an LMI. And so it's worth going through. And the sufficiency part, in general, this page is sufficiency, is easy, very easy. Necessity is also relatively easy, but it's a little bit more complicated. But it's also very interesting, so we'll cover that as well. So the reason that LMIs are so useful for systems analysis and control is because there's this one-to-one relationship between positive matrices and positive Lyapunov functions. So positive quadratic Lyapunov functions in general. So in particular, if P is a positive matrix, we immediately think in terms of a positive Lyapunov function. So if we define this Lyapunov function x transpose Px, right, it's a candidate Lyapunov function if and only if P is positive definite, right? And that was sort of the definition of positive definite we went over in the previous lecture, right? So that's greater than 0 for x not equal to 0 if and only if P is greater than 0. P is positive definite function. That's, if you recall, actually the definition of what a positive definite matrix is, right? So there's this one-to-one relationship between positive matrices and positive Lyapunov functions, positive candidate Lyapunov functions, I should say. So with that in mind, right, of course, the proof structure is relatively straightforward, right? I mean, if P satisfies the LMI 1, I'll write that down again, then obviously P is a candidate Lyapunov function, right? Because it's positive definite by definition of positive matrices for any x not equal to 0, and of course at x equals 0, it's 0, right? Because, right, look at it, right? Plug in 0, it's 0. Furthermore, right, if we take its derivative now, and this is I guess a little bit more complicated, but not too much, right? You take the derivative of this Lyapunov function, right, just by the chain rule, v dot equals, well, there's x dot, and then px is the rest of it, and then by the other half is x transpose p, and then x dot on the other side, right? So that's what we have here. And then we just plug in for equal to ax, right? And then this x dot becomes ax, right? This becomes that. This becomes that. And we factor x out on the left and the right, and then we get x transpose a transpose p plus a times x. And of course, this is negative definite if and only if a transpose p plus pa is negative definite itself. Again, by the definition of what a negative definite matrix is. So we conclude then, right, that our Lyapunov function, our quadratic candidate Lyapunov function, is strictly negative. Therefore, the system is globally stable, and globally stable is equivalent to A being Hurwitz. So this allows us to translate, or at least in a sufficient condition anyway, in this case, right now, for stability or that property of the system. Okay. So I think we talked about that. The converse direction is also interesting, right? So here we didn't have Q here, right? So let's say, for example, Q equals identity, right? So in that case, right? So it doesn't matter. Q identity, the matrix is positive definite. Where do we get our Lyapunov function? Well, I mentioned, right, that if, right, the trajectories of the system look like this, then a good choice way of thinking about Lyapunov functions is this length, the length of the line that is left, right? So this is x of t, right? A good way of thinking of the Lyapunov function, v of t, is the integral from 0 to infinity of x of t. Let's take its norm. That's the norm, by the way. So the magnitude squared dt, right? And of course, we were using t on the left, so it wouldn't make much sense to use it on the right. So we'll make that from t to infinity and make this a dummy variable, which we'll call s. Right? Okay. So this is a pretty straightforward looking Lyapunov function. It's just a line left. But how do we get from there to equal x transpose px? Well, in linear systems, we have this very nice property, right, that x of t is e to the a t x naught. And so we'll just replace t here with s, right? And then our v of t is, right, integral from t to infinity of, and here we'll just start, at x of t, of this, the norm here, which is x of t transpose x of t, d, and we should do s, not at t. And then just plug in for our solution there, and we get integral from 0 to infinity of x of t e to the a transpose s. And here we use that transpose property that we had before, e to the a s, x of t ds. And here we'll just, because we're starting at 0, just make 0 initial time, 0, 0, and so v of x is, just make that x, right. Oops, x. Right, and so what's nice is, of course, we can pull the x doesn't depend on s, right? It's the initial condition. So we just pull that out, x transpose, and we have integral 0 to infinity of the matrix exponential itself. And there's an x here. And we'll just call that, right, p, and then we're done. We have a Lyapunov function, x transpose px. And as we argued here, right, the length of the solution is decreasing with time, and so it stands to reason that that's going to be decreasing. So now that's what this proof is, right? So we specifically propose this value of p here, motivated by this. And now, of course, right, it has a q in the middle, but again, we could choose q equals identity. This is just sort of a generalization where we replace this with like x transpose qx, right? So it's a different metric for the length of the system, but they're all equivalent. It doesn't really matter. But right, so we can now propose this Lyapunov function and take its derivative, and then we'll get this inequality here. The proof here actually takes a slightly different, more algebraic approach to the problem. Specifically, if we multiply p times a, right? Well, then a comes here on the right, and it's multiplied by this integral, and so our first, because a commutes with all of the powers of the exponential, we can actually move a to the other side. And then, well, what do we have here? Well, what is this? This is x dot with respect to s in this case. And now we use integration by parts. This is dv, this is u. So integration by parts says u dv equals uv at the boundary minus v du, right? And, well, that's the integral. And so that's what we apply here. This is dv, this is u. I already did that. And so we apply that. This is now u, this is v, right? So obviously v is just this part, right? And so at the boundary 0 and infinity minus v du, and so this is du, and this is v, right? And missing a ds there. So now we examine this term here. Well, what is that term? So that's at infinity minus at 0. Well, at infinity, this term goes to 0. E to the a infinity equals 0. And so that term, this term gets disappeared. Minus at 0, well, at e of a 0, that's just identity. And so we get this term here. And then minus this term over here. Well, we know this is equal to a e to the a transpose s. And so we can just plug that, a transpose, just plug that matrix property there, and we get that we have this negative q here still popping out, and minus a transpose p. So pa equals negative q minus a transpose p. We just pop a transpose to the other side of the equation, and we get pa plus a transpose p equals negative q, and of course q is positive definite, so minus q is negative definite. And so we obtain LMI 2. Right? So this is more of an algebraic proof. This is the conceptual proof. But in any case, we get to the same point, right? Feasibility of the LMI expressed in a way which we can then use in YALMIP. So we've now proven our first LMI. We've taken a first step to transferring properties of the solution to properties to an LMI, to a convex optimization problem. Right. So here's just some notes. Sufficiency, necessity. This is like the conceptual idea that I was talking about on the previous slide. So that's continuous time. We have one LMI. We like to pose lots of LMI, so we might as well do it in discrete time because it works actually even easier. It's even easier in discrete time, so we might as well generalize it. To do that, of course, we need to define Lyapunov functions for discrete times. However, the concept is more or less the same. The conditions for Lyapunov function to be a candidate Lyapunov function are the same. Same candidate constraints. However, there's no continuous dynamic, so we can't take the derivative of the Lyapunov function. And so, in fact, actually, discrete time systems are discrete, right? They jump from state to state, jump from here to here to here. 1, 2, 3. And so our condition then becomes not that it's continuously decreasing, but that the Lyapunov function decreases from time step to time step. So specifically, it decreases at every time step, so that v of 2 is less than v of 1, and of course v of 3 is less than v of 2, and goes so on and so on. So every value, at every time step, the Lyapunov function is strictly decreasing, right? So strictly decreasing. So Clearly, right, if you think in terms of energy, if it's strictly decreasing at each time step, it's going to approach 0. The Lyapunov function will. And if the Lyapunov function, if it's a candidate Lyapunov function, goes to 0, then the state itself will go to 0 as well. And so if you can find a candidate Lyapunov function which is decreasing at each time step, then the system is stable. So we apply this to, again, this exact same logic as before to obtain our second LMI, which is a necessary and sufficient condition for sure stability of, for surety of the matrix A. Now remember, surety of A is a property of A, a property of a matrix, but of course we've shown that it's necessary and sufficient for stability of the discrete time system. So basically it's the same deal as the first LMI. A is sure if and only if there exists a P greater than 0, right? So that implies that that's LMI 1, LMI constraint 1, and that ensures that P defines a candidate Lyapunov function. And then we have the second LMI constraint here, which ensures that the candidate Lyapunov function is decreasing at every time step. Right. And again, sufficiency is relatively easy in this case, right? We define the candidate Lyapunov function, x transpose px, exactly the same candidate Lyapunov function as before. It's a candidate Lyapunov function for exactly the same logic as before. Now, the derivative, we don't have a derivative, we have to advance it at each time step. So if we advance the Lyapunov function at a time step, right, so v of k plus 1, well, we can write that out. Well, what is it? It's like transpose k plus 1, p x, k plus 1. And of course we have we know what x of k plus 1 is. It's just a of x of k. And so we plug that in, right? And so we get a of x of k and a transpose a of x of k. And by our Lyapunov inequality, right, this is equivalent to a transpose pa less than p, right? By the definition of, right, inequality, the matrix inequality, we have that, right, this is strictly less than this term here, x k transpose a transpose p a minus p x k is less than 0. And so that gives us that the Lyapunov function at time step k plus 1 is less than x k p x, which is the Lyapunov function at time step k, right? So we have that the Lyapunov function decreases at each time step, which implies that the system is stable because it's sure, right? So, or these are equivalent. Right. So that's a sufficient condition for stability in terms of an LMI. It's easy to show it's necessary by the same logic that we went over in the continuous time case, right? In this case, our Lyapunov function, right, is the sum of all of the future time points. So if this is our trajectory here, which is sort of discretely curving into 0, it's the sum of all of these x of k, x1, x2, x3. So our Lyapunov function, right, is the sum k equals 1 to infinity of xk transpose xk. Right. So in terms of, again, we use sort of a more algebraic style of proof, but you can show, right, that this yields the Lyapunov function x transpose sum a transpose k a k equals 0 to infinity. And so we plug that Lyapunov function in here, right? And we actually prove it algebraically here. So we take A transpose PA, because I guess the proof is a little bit easier. And then when we apply A on both sides of this, right, well, that just advances the power here by 1. Right? And so actually we can just change our indices, right? Instead of starting at 0, we start at 1 and we get the same form, right? So now it's a sum from 1 to infinity, and then the Lyapunov function itself, P, right, is the sum from 0 to infinity. And so every single term in this series cancels except for the very first one, k equals 0. And so the only term we have left that's non-zero is this k equals 0 term. And so we plug in k equals 0, and this becomes, of course, the identity. This becomes the identity. And the only term we have left here is this negative q. So A transpose P minus P is equal to negative q, which in q is by assumption positive definite, so this term is negative definite, right? And this works for any q, so I mean, don't get confused on the q, right? The same proof would work for just using q equals the identity, right? That's just as easy. Right. We just proved it in generality because that's how these things are done. Right. So now we have 2 LMIs now, one for Schur stability and one for Hurwitz stability. Just to give you an idea of how these are implemented, it's showing it's not hard. Just to give a little brief LMI code, YALMIP code here. So basically P, make P a variable here. P is your variable. Declare it to be an SDP var. If you don't give any more commands to SDP var, it's going to assume it's symmetric. So that's we do assume it's symmetric here, so not a problem. Now to make it a candidate Lyapunov function, we have to make it P strictly greater than 0. And the strictness, right, is important. It's something that people get wrong all the time, and I want to emphasize it so much because I really don't want to hate it grading homeworks based on that. But to make P strictly greater than 0, right, you've got to add some non-zero term to it, right? You have to make it strict in some sense. How strict? The solver doesn't know how to interpret strictness unless you tell it exactly how to interpret strictness. So I just chose arbitrarily a strictness constant 0.1 here, right? You could choose, if you're worried, you can choose 0.001, right? That would also be okay. Or anything which is not 0 and greater than machine precision, right? So probably 10 to the negative 15th is not okay because it can't really tell the difference between that and 0. But negative 3, fine, right? So this makes it a candidate Lyapunov function, valid candidate Lyapunov function. And then we have our second LMI here, which makes it decreasing. And so this can be non-strict. That's okay. If you're not interested in strictness. Or you can add strictness, whatever, however you like. Then in that case, it would be less than or equal to negative 0.1 I. Don't forget the I here, right? That's the identity matrix. Right. And then you push, so you add your first constraint, then you just append your second constraint to that using this semicolon, and then you have both your constraints. There's no objective function, so you just hit optimize and you're done. Right. So again, very straightforward implementation of these LMIs using YALMIP. Right. Okay, so next, again, right, what I talked about in the slide. I do mention that actually, unlike the Hurwitz condition, this is actually quadratic in A. A is not a variable, so at this point it doesn't matter. It will become more important later, so we'll have to talk about that. So again, we've transformed two system properties to properties of the representation, and then we've taken that representation and constructed a convex optimization problem which proves those properties. So in the next section here, which I'm going to take a quick break before we do, because it's a natural stopping point, we'll apply this to more properties other than just stability, some additional properties, again, which are defined using the eigenvalues, but again, using the representation. But again, I'll stop here for a second before starting again.